So see, I already defined when a pre-variety is called variety, right? Pre-variety is called variety when this diagonal map. See this map is this map. So now you know the product of variety exists. So now there is a map, canonical map, because you take the identity map x to x, x to, so x cross x to x, right? So then there is a canonical map from x to x cross x, and if this map, the image of delta x, if this is in x cross x, if this is closed, then you call x is variety.
Separated.
Yes. So this is also equivalent of saying that if we have two functions f of g, f and g, and y is any variety, y is any variety, and f and g are two morphisms from y to x, then the set of points y where they are same, this is a closed set. Right? This we have seen all this. So now what I want to define, so these are, so I will not say, I will come back now again. The working with pre-varieties is a little sticky, right? Sticky in the sense that it's not a okay. Mostly I will again come back to the affine variety, but I have to do it because of that reason, that when you define this map, that Pn and this Pm, and you consider this Pn cross Pm, which is a Segre variety, that so what you had to, so you have this map Pn cross Pm to Pn and Pn cross Pm to Pm. Now, okay, this is not the thing. So this is some Segre variety, right? Pn you embed it into some P large of Pn m plus n plus m, right? This is the map. And similarly, sorry, Pn cross Pn. You embed it into this, and there it will go to some equations, right? You have some homogeneous equation, and so this will actually lie in some closed subset, so homogeneous polynomial, and so it will. So this was our product, Segre product, and now you have to show that this from say this Segre product to Pn, there is a natural map, right? So how do you define that? So then, so now you have this this P. This you call it P. First of all, what is this projection map? That also I did not define. I think last class. So P1 and P2. So you have to define something from this to Pn, right? So what you do, you take the affine cover. So P of n, you can write it as some affine, the standard affine covers. Then you take, you call this Z, say Z prime. Now this Z prime intersection Ui to Pn, you have defined map, and Pm. And now you see that they glue on the intersection. So you define two maps. So this is say P1I. Now this P1 0, P1 1, P1 n. You define these maps, and now you show that these are this glue. So that will give a map from to Pn. That's how you define, right? And similarly for the other case, P2. Or P2J, P2, I mean, this is P1. So this is how you define the map. And then, so first I want us to do that. And then what you have to prove that if you have a map from Z to PM and Z to Pn, then you have this set theoretic map. If suppose this is R and this is S, then you define R comma S to this. And then you have to show that this is a morphism. But Z is an abstract variety. So what you do, so first you do Z is union of affines, say AIs. Now you prove that from if Z is affine, then you can do this. Then this is a morphism. And then you use the previous proposition to show that this is a morphism, that if Z is union, so it's a morphism. So a lot of checking. That's why I say that anything you want to do, any proof you want to do here, it's like moving a rock. You need to check it at every step, whether it's a morphism, because it's the concept of morphism is little tricky in algebraic variety, especially when you are dealing with projective varieties or more general varieties. At the affine level, but everything is from affine level. You see, the base is the affine pieces. So always you have to break it into affine, and then you see that at affine level it is going well, and then you have to adjust your argument so that it is working well at the global level. So that's how. Okay. So I needed this morphism of prevariety just to convince you that there are a lot of work to be shown here, that this is a product of projective variety, right? It's not easy. It's not coming free, like in the affine case. Affine case also you have to prove, but it was easier, right? Okay, so now or maybe I will stop here and I will continue in the next class. So what next class I'll do mostly I'll come back to now see what I wanted to convince you, that something is morphism is very sacred, in the sense that it's not a God-given thing. It's really you struggle to construct a map. So once you have such map, when something is how do I say, when something it's hard earned, you try to analyze that. That has a lot of richness, right? So now you study the properties of morphisms. So what do you mean by that? That means if you have a map from X2, so what is the simplest morphism? Simplest morphisms are isomorphisms. We use isomorphism. But if it is not isomorphism, then simplest map is that if the fibers are finite. So these are called, in algebraic, they are not called finite morphisms, they are called quasi-finite. Even when X is affine, in the case of X, Y, both are affine. In this case, in this case, if you have a quasi-finite map, that means fibers are finite, then you can talk about at the ring level, AY to AX. Now, this is AF and this is F hash. Now, you can talk about this F hash of AY. Of course, this is subring of AX. Now, that means what kind of properties do they have? If AX is integral over this, now you know the going up theorem, right? Going up. So that will say that fibers are finite. That if you have a maximum, they are finitely. So I don't know whether you remember, in first few classes I did going up theorem. I'll use going up theorem to say that if the fibers are, if this is integral, then you say it is a finite map. And now you can generalize this for any variety, projective variety, say any variety, x to y, it is finite. If y has a finite cover, affine cover, and inverse image, if you take the inverse image, they are also affine, and if this is map of affines, they are finite. So locally they are finite maps. Then the map x to y is a finite. Everything, do it first at the affine level. So this is the philosophy. You do it everything at the affine level, and then you try to globalize. That locally it is, even in manifold, in differential geometry also you do the same thing, right? You do it at the Rn and to Rm. Everything is like Rn to Rm. Here it is just affine varieties. It is not An, but some subvariety of An. Okay, I will stop here.